Okay, so this is our worked example for the concurrent forces example in the notes. We've got three forces all pulling away from a central point. We know two of the forces, we know their direction, the angles, and we know their magnitude, the size of the force. We've got one unknown F and the unknown angle of theta, so that's what we're going to calculate over the course of this example. So the first thing we're going to do is we're going to take our angled forces and we're going to pull them out individually. So there's my 8 kilonewton force. And we're going to resolve these into its horizontal and vertical components. 12 kilonewtons, and then I've got force F, which I'm going to include as well, and its angle theta, 12 kilonewtons at 50 degrees. Okay, I'm going to split these up in the way I did previously. So my horizontals, I'm going to keep green. So there's horizontal there, horizontal there, I've got horizontal there. Remembering that we need to contain the angle within the triangle. And verticals are going to be reds. These two are going up, and this one here is going down. So now I'm going to go through and label these using my my trig values that we talked about before. So vertical in this case is opposite the angle, so that's going to be 8 sine 30. In this case it's opposite again, so 12 sine 50. And this one we're going to call FV, the vertical component of F. Horizontals now, these two are adjacent, so we're going to go 8 cos 30 and 12 cos 50, and this one we're going to call FH, the horizontal component. We're then going to use our laws of equilibrium, and we're going to balance our vertical and horizontal forces. So start with vertical. So vertical. Sum of the forces vertical equals 0, forces up equal forces down. So forces going up, I have these two going up and FV going down. So 8 sine 30 plus 12 sine 50 are equal to FV. Therefore FV equals 13.2 kilonewtons. I'm going to do the same with the horizontal now. So horizontal, so sum of the forces horizontal equals 0, forces right equal forces left. So going right, I have 12 cos 50, and going left I have, so that's equal to 8 cos 30 plus FH. So to get FH on its own, we're going to take 8 cos 30 away from both sides. So 12 cos 50 minus 8 cos 30. So FH is equal to 0.8 kilonewtons. Now because this is a right angled triangle, and we want to know F, which is the hypotenuse of it, we can use Pythagoras to figure that out. So we know that Pythagoras is c squared equals a squared plus b squared. So in this case, we are going to use Pythagoras. We're going to use it to find f squared, or f. So f squared is equal to fv squared plus fh squared. So f is equal to the square root of fv squared plus fh squared, which equals the square root of 13.2 squared plus 0.8 squared, which equals, you stick all that in your calculator, 13.22 kilonewtons. Very close to our vertical component. Okay, so that tells us that that angled force F is almost vertical. What we're going to do now is we're going to figure out our angle, our direction. Okay, and to do that, we are going to calculate that using the inverse tan function. The reason for that is, if we think back to our SOHCAHTOA, we have both the opposite component FV and the adjacent component FH. So we're going to use the inverse tan function to get this. Okay, so theta is equal to the inverse tan of the opposite over the adjacent. So that's inverse tan of 13.2 over 0.8 which gives us an angle. Gives us an angle of 86.5 degrees. Okay, so our final answer there is that F is 13.22 kilonewtons at an angle of 86.5 degrees.